All right. We already talked about kinematics of rigid bodies. We covered that. We talked about mass moment of inertia and what it is and why do we care about mass moment of inertia when it comes to the motion of rigid bodies. Now, I'm going to start talking about dynamics of rigid bodies, and specifically we'll be focused on the dynamics of rigid bodies when it comes to the motions of rigid bodies in a plane, like in a 2D space. So when we were talking about the dynamics of particles uh, back in the first part of the semester, I mentioned that when it comes to dynamics, we usually consider two subcategories for dynamics: kinematics and kinetics. We said kinematics is the part that we deal with positions, velocities, and accelerations, and kinetics is the branch that we deal with forces and torques that cause the motion. So when we start looking into the dynamics of rigid bodies, we have to consider both. We have to consider the kinematics that we talked about that before, and we have to add kinetics to the whole analysis. Then we will be able to study dynamics of rigid bodies when they move in a plane. So we are going to follow pretty much the same classification that we used for dynamics of rigid bodies, for kinematics of rigid bodies, sorry. We're going to classify the motion into translation, into three groups: translation, rotation about a fixed axis, and at the end, we're going to look at the general motion of rigid bodies in a plane. So let me just briefly put it here. I guess it's not that bad to do a review about this part too. So dynamics, this is to study dynamics of rigid bodies, we have to look at kinematics and kinetics. Kinematics is what we were doing before, right? We were studying the kinematics of rigid bodies previously. So this is just a category or a subcategory, I would say, that deals with positions, velocity, and accelerations. So let me just write it here. Deals with velocities, positions, and accelerations. As I said before, when we are studying the kinematics of rigid bodies, or generally studying kinematics, we don't really care about the forces and torques that are causing the motion. We just care about how does that particle, or in this case, how does that rigid body move? How does it accelerate? How does this velocity change? But when we look into kinetics of a rigid body, we care about forces and torques that are causing the specific motion that we're looking into. So let me just put it this way: deals with forces and torques that cause the motion. Now, as I said, we're going to follow the same classification that we used when we were talking about kinematics of rigid bodies. So I'll write it this way: we classify the rigid body motion, the rigid body motion, into three categories. It can be translational, can be rotation about a fixed axis, and fixed axis. And eventually when we have both translation and rotation, that would be general planar motion. General planar motion. We talked about these categories before. If you take a look at the video and lecture notes for the session that we were talking about, we started talking about the kinematics of rigid bodies, and we mentioned the characteristics of each category. For translational motion, if you remember, we said when we were talking about translational motion, pretty much every point on a rigid body has the same velocity and acceleration. So I'm going to start with translational motion. Let's take a look at translational motion first. Translation. I'm not going to repeat whatever we talked about when we were talking about translational motion in kinematics of rigid bodies, when we were studying kinematics of rigid bodies, so you can just review your notes. But when it comes to dynamics, what we do is that, well, we know about the kinematics of rigid bodies. We know how to deal with that when it comes to translational motion. What we need to do now is to just add the forces and torques into the whole analysis. So we're going to use what we always use when we want to relate the kinematics when we want to relate kinematics to dynamics, right? We're going to start with Newton's second law. We're going to use Newton's second law to study the motion. And since we are studying the motion of a rigid body, we are going to specifically study the motion of the center of the mass of a rigid body. Right? So it's pretty much similar to what we were doing when we were dealing with particles. Now, our particle is the center of mass. So we are still studying a particle, but that particle in a rigid body is the center of mass for that rigid body when we are dealing with the translational motion. So let me put it this way. We can use Newton's second law to study the motion of the center of the mass of a rigid body. Oops. Just about there. So what was that? This Newton's second law was telling us the summation of all the forces applied on the mass. In this case, is a rigid body, and the forces applied to rigid body is equal to mass multiplied by the acceleration. So this is the first equation that we use when we are studying a translational motion. Now, since we are dealing with a rigid body, as I said before, the difference between one of the main differences between a rigid body and a particle is that we care about how the mass is distributed. So we care about kind of the geometry of the body. It's not just a specific, it's not just a particle anymore. So what we need to do is that we have to figure out also the balance between forces applied at different parts of this rigid body. Right? We know it's translational, so there is no rotation. Right? There will be no rotation during the motion when we are dealing with a translational motion in a rigid body. So all the forces applied to that rigid body, they should be in balance when we find their moments about the center of gravity. Right? If they are not in balance, we are going to see some rotation in a rigid body. We're going to have we'll have to have some kind of rotation above the center of mass. Since it's translational and there is no rotation, so the moments created by all the forces applied to a rigid body at different points, right? They all should cancel each other out. Otherwise, we're going to have a rotation. So there is an extra equation that we are going to add to our analysis, and that would be also, let me write it this way. Also, since there is no rotation, summation of all the moments applied to a rigid body at any point, not just center of gravity or center of mass, because if we have a force that is not balanced with another force, we are going to see some kind of rotation about some point on a rigid body. Since there is no rotation, this means that if we sum up all the moments created about a specific point on a rigid body because of the forces applied to that rigid body, that sum should be zero. So we have two equations now to analyze the motion, the dynamics of rigid bodies that are going through a translational motion. This one, F is summation of forces is equal to ma, and summation of all the moments around the specific point should be equal to zero. So let's take a look at, before I go there, this is nothing new. Right? It's like studying the particles, studying the dynamics of particles, except this time we are focused on the center of mass of a rigid body. The only thing added is this equation, which pretty much gives us an extra equation. This means that we can afford having an extra unknown. So before we could write this equation in x and y direction, right, which means we could have two unknowns. Well, we're talking about the motion in a plane, so we only have two possible directions. We can choose two possible directions for the motion x, y, or any other r theta, a tangent normal. Right? So we can do the same thing here. This equation gives us the capability to find two unknowns by itself, and then we're going to have an extra equation for the moments that they should be zero. It means that we can afford having an extra unknown possibly in our problem when we are analyzing the translational motion of rigid bodies. Now let's take a look at an example, see how does this work.